All right. Hello, everyone. I'm Siddharth. I am a PhD student here at the University of Waterloo. I'm part of the data systems group, and I'm here to talk about why graphs are exciting. So I'll begin with a story. This story is in the city of Königsberg in Prussia, which is now in Russia. And it had 7 bridges across the river Pregel. And they didn't have Twitter or Facebook or Instagram at that time. So people used to think about less exciting things, like what can we devise a path which crosses all the 7 bridges, but it only crosses them once and not more than that, right? So that's the problem they were thinking about. And they tried different things. They tried different ways to cross the bridges. They couldn't find an answer, but they didn't know if it had an answer or not. Enter Leonhard Euler. He was a brilliant mathematician. He has a lot of contributions in his name. He started thinking about this problem. And to do that, he reduced this problem to its simplest components. So we don't really have to think about the land and the bridges and the river. We only have to think about the 4 pieces that the bridges connect and the bridges themselves. So once we have the 4 components, we can remove that. And then we just add the bridges that connect these 4 components, right? And voila, we have a graph. So what is a graph? It is just one particular way of thinking about data, of representing data, right? In this particular case, you have a vertex, and you have an edge that connects these vertices to represent some relationship between the vertices. In this case, it is a bridge which connects land masses, right? And you can also add data to these vertices, like is it an island or a mainland? And you have a graph. Note one thing, that the edges in this case is undirected. You can cross the bridge in any direction, right? Now, let's say you come to the 21st century and you have traffic problems. And the city decides that you can only cross the bridge in one direction. So you add some direction to the bridge, and then you have a directed graph. Right? This is just 2 kinds of graphs that we have. Now, what can we represent as graphs? Surprisingly, a lot. I'll give a very few examples, the most prominent of which is social network. We all use Facebook and Twitter. And the graph is very inherently the data is very inherently graph-like. You have people and you have connections between people, right? Similarly, financial transactions, where you have accounts and you send and receive money across accounts. Web, you have web pages and then you have links between them. Similarly, you have biological networks, where you can have proteins, and which proteins interact with each other can be represented as a graph. IT infrastructures, like servers, applications running on them, packets that are being routed through switches and routers, can all be represented as one big graph. And finally, geographical maps, like points and roads between them, is very easily represented as a graph. And this is just 6 examples, but there are a lot more data that naturally lend themselves to the graph structure, right? So we have this data, but what kind of queries can we run on top of them, right? So I will give an example of 3 queries, the first of which is a subgraph query. And that is essentially looking for patterns in my graph. So imagine you have Twitter data, where people follow each other. And Twitter wants to recommend new followers, right? So one way of doing that is to look for diamond patterns in the graph. So you have a person A who follow 2 people, person B and C, and they both follow person D. And if you find this pattern in the graph, then it's probably a good idea to recommend that A should follow D, because 2 of your followers are following person D. Right? So this is a very graph-specific computation you can do. Similarly, shortest paths. Like I want to attend Starcon, I want to go to M3. OK, Google, navigate me to M3, right? And Google says, hey, let me do a graph query for you and find the shortest path to M3, right? The third example is neighborhood queries. So if you are on LinkedIn and you visit a profile, LinkedIn will say, hey, this is a 3rd-degree connection or a 2nd-degree connection, right? So that's you. 1st degree, 2nd degree, 3rd degree, and so on, is a very natural graph query to perform, right? So in general, when do you think about graphs? You think about graphs when the data that you have can be very easily represented as entities which has relationships between them, right? And it's very easy to think about data and relations between them. And you have queries that use this inherent network data to extract meaningful information out of it, right? For example, just to show the difference in which graph versus a normal way of thinking. So we have the Twitter data again, where people follow each other. So Dan follows Emma, Emma follows Bob, and so on. The same data, so this is a graph form of the data. The same data can be represented as a table. So there's a table from to 2, and Emma follows Bob, Meg follows Dan, and so on. Right? So these are two different ways of thinking about the same data. Let's say we want to perform a query on this data, which is find all 2-degree connections of Meg. Right? You are in LinkedIn, you want to say, what are my 2-degree connections? Let's first see how you do this using the table. Right? So what you have to do is you use the same table 2 times, and you do something that's called a join of the table. If you are using relational databases, then you know what I'm talking about. But the idea is you have Meg, and then you find the 1st-degree connections of Meg, and then you find the 2nd-degree connections in the second table, and you join them, and you find your answer. Right? And I will show you the query to do this. If you're not familiar with SQL, don't be afraid. It's just to show you how complicated and unnatural this seems. Right? This is SQL, which is used to do this query. Let's see the same query using graphs. Right? So you have the graph. You can directly find all 1st-degree connections of Meg, which is Dan and Ivy here. And then using the same structure, you can say, oh, what are the 2nd-degree connections? So from Dan, you directly go to Bob and Emma, and you have your answer. Right? So when you're thinking about this data and you're thinking about your query, it's more natural when you have the graph structure as compared to table structure. Similarly, when you're writing the query, this is in a language called OpenCipher, where you simply say match A to B to C, where A.name is Meg. And if you compare it with the SQL query, this is a more natural way of what you wanted to actually get, right? So that's good. You have graph data, you have graph computations, graph is a more natural way of doing things, and you jump right in, right? But what are the challenges you can expect to face when you're working with graph data? So I will point out 3 challenges. The first of which is scalability. So once your data is small, like the one I just showed, it's very easy to work on that. But because graph databases have not been developed so much right now, and because scaling graph data is inherently hard as well, so this is part of our universe. So this is the galaxies and clusters of galaxies, and people are trying to represent this as a graph as well. Right? You can go to this website, Cosmic Web, and they are trying to do this. And this is an inherently hard problem. Like when your data is very large, how do you deal with that large amount of data? So that's the challenge. The second challenge is visualization. So graphs very naturally lead to visualization, right? So if you look at graphs, you can probably just eyeball the data and find patterns into it, find nodes that look very important. And this is also a challenge, because how do you highlight such important patterns? From very large graph, if you can manage to cluster the data into their common components, then it's probably easier for people to find patterns. Right? Or maybe you want to represent the data in this particular way so that the components that are related to each other are clustered together. Right? So that's another challenge that's being actively worked on. The third challenge is query languages. As I showed, even though SQL looks complicated, it's very popular these days. A lot of people know how to do SQL. But graph languages, not so much. I showed you OpenCipher, but there are other languages that you'll come across if you start using graphs. For instance, Sparkle and Gremlin. And all these lead to different ways of thinking about graphs. And there is no standard graph language that you can use right now. And that's another challenge you might face. However, even given these challenges, graphs really will be important part of the future because of problems like this. The knowledge graph. Google is trying to answer queries using natural language, right? Like who was the president of the United States in 1979 and so on. And the knowledge graph is how Google actually answers these queries. Retail, like Amazon wants to recommend products that you will absolutely buy. And what they do is they look at what products customers have bought and then bought together with them, what customers are friends with each other, and so on. And all this data can be represented as graphs, and that leads to better analytics. Similarly, security and fraud analysis. Like that's another very key component of the future analytics that people are interested in. And the Internet of Things. You have so many devices and so much data that's coming in, and that can all be connected into one large graph, and important data can be correlated together. And graphs very naturally lead to all these kinds of queries, right? So how do you get started? There are lots and lots of graph databases out in the wild, both open source and closed source. Very recently, this Tiger graph was released, which claims to deal with 100 billion vertices, 600 billion edges. That's like a very large graph that they're working with. But if you want to get started, I would suggest that you go for Neo4j, which is a very popular and very easy to get started with. They have a visualization tool, and they have like step-by-step tutorial which you can just dive into to start working with graphs. Another thing is our research that we are working on. We built a new graph database from scratch, which is called GraphFlow. And to give a very brief overview of what we are doing is we are looking into continuous queries. So what are continuous queries? So let's first look at one-time queries, right? So you have an application, you have the database, you ask, give me all triangles in the graph, the database responds, okay, here are your 2 triangles, and you're done, right? And there's no state between the database and your application. Now let's say an update comes in and you want to find new triangles, then you have to do the same query again, get the data, get the results, or this results I had seen before, and so on, right? So we don't want to do that. What we want to do is tell the database, continuously match triangles for me. And the database says, okay, I will keep looking for triangles for you. And as soon as an update comes in, the database will automatically tell the application that, hey, here are new triangles that are come in the graph. Or if a triangle gets deleted, hey, this triangle which was previously there is not present anymore. So this is something that our graph database is able to do. Here's our website, and it's an open source project on GitHub, so you can go check it out, contribute if you like. Okay, coming back to the story that I began with, I never finished that. So Euler used this graph structure to actually show that the problem has no solution, right? So if you look at the degrees of the vertices, and degrees means number of incoming and outgoing edges, right? So in this case, all the vertices have odd number of degrees. And what Euler showed that to solve this problem, the maximum number of nodes that can have odd number of that can have an odd degree is 2. But in this case, there are 4 vertices with an odd degree, so there is no solution to it. However, if you remove an edge, which I did from 1 to 2, now there are 2 vertices with an odd degree, and this can actually be solved. And like one solution is you go from 2 to 4, this to this, and you're done. So that was my talk. Graphs are really exciting to work with. That's what I'm doing in my research, and I hope I got you excited too. Thank you very much.